Assalamualaikum warahmatullahi wabarakatuh. Selamat hari. Saya tuliskan chapter 8 ini. Proceed with the structural design. Okay, the first slide. Element analysis. Now, in plastic part design. So, this technique it provides valuable information about the mechanical performance of complex or critical design. So, I'm sure you are familiar with you have experienced how to use analysis. For simple geometries and non-critical parts, standard design formulas can give a good result if the material remains within its elastic limit. Okay, even in a complex part, an area or feature under load can often be represented by standard formula. So, because they are primarily a function of part geometry and load and not material properties, stress calculation formula derived from metal apply directly to plastic. Okay, generally, material dependent deflection formula require elastic ataupun Young modulus and sometimes Poisson ratio, which is given by the symbol U. Okay, Poisson ratio varies slightly with condition, but usually only to an insignificant decrease. Okay, we look at the use of moduli. For short-term loads at temperature and stress level below a resin proportionally, use the instantaneous elastic modulus. Okay, at other temperature, use isothermal stress strain curve to calculate the elastic modulus. Okay, kalau dekat room temperature, dekat room temperature, kita guna um, kita boleh direct measure dia punya yang modulus lah. Formula dia kan kita belajar kan, kita boleh kira je. Kalau dekat other temperature, kita kena guna isothermal stress strain curve untuk kita kira elastic modulus, which is the simply stress divided by strain in the linear region at the desired temperature. So simple bending calculation is involving solid plastic undergoing short-term loading below the proportional limit can use either the flexural modulus or the published instantaneous tensile modulus. Untuk short-term load in the non-linear region above the proportional limit, such as assembly stress, we will have to use a secant modulus, which is calculated from the curve and based upon the actual calculated stress. So to calculate the secant modulus, first solve the stress equation, which is independent of the elastic modulus for the material. Yang macam sebelum ni, slide sebelum ni saya dah tunjukkan macam mana nak kira, macam mana dia punya cara kita cari modulus tu kan, secant modulus tu. Kita plotkan dia punya straight line dekat curve yang kita dapat tu. Okay. So to calculate the secant modulus, first solve the stress equation, which is independent of the elastic modulus for the material. Next, rate the strain corresponding to this calculated stress with the appropriate stress rate curve. Then divide the calculated stress by the strain to obtain the secant modulus for that stress level. So for the secant modulus, typically it provides prediction of deflection in application that experience higher strain level. Kita tengok unit geotensile and compressive stress. Okay, because most plastic part failures are tensile failures, and this failure mode is easy to test, so the majority of the available stress strain data were produced using tensile. Compressive strength of plastic usually exceed the tensile strength, but because it is more difficult to test, so the compressive strength is usually assumed to equal the tensile strength, which is a conservative assumption. Depending on geometry, excessive compressive stress may cause the part to buckle. Long, slender shapes are the most susceptible to this failure mode. Consult a strength of material. Okay. So dekat slide ni kita ada beberapa calculation yang awak boleh cuba buat lah. First, ni adalah soalan berkenaan dengan tensile stress and strain. So given a 5-inch long macrolon polycarbonate bar with a cross section of 0.5 inch by 0.125 inch is exposed to a 250-pound tensile load, which is produce a non-linear stress strain curve. Okay, try kira first stress of the PC bar. Kita nak kira stress. Okay, so the definition of stress is load by cross-sectional area. So awak kena cari cross-sectional area dulu. Berapa dia punya cross-sectional area? 0.5 times with 0.125. So dapatlah dia punya cross-sectional area A. So dia punya load dia dah bagi dah 250. So 250 divided by cross-sectional area. So you will get berapa? Okay, MPI. MPI ataupun PSI. Okay, secondly, calculate the inclination of the PC bar. Assume yang modulus for PC is 350,000 PSI. Okay. So, to find the elongation of the bar, you need to determine the strain. Okay, pemanjangan, change in length. Okay, change in length per unit length, which is given here. Dibagi yang modulus. So, awak kena cari elongation dia by using the yang modulus. Okay, so cara nak kira dia sama dengan awak kena ambil nilai yang awak dapat dekat A ni, stress over dengan stress over yang modulus. So you will get 0 point something, then times with 100 and you will get the percent strain. Cuba kira, nanti saya akan bagi dalam test, jalan test. Saya akan share jawapan dekat dalam WhatsApp nanti. Alright, for C, calculate the secant modulus of the PC bar. Assume a value of 1.35% strain for a stress of dia minta awak cari secant modulus berdasarkan load yang dia bagi dekat load yang awak dapat dekat A ni. Awak dapat A ni, load dia berapa, stress dia berapa. So awak kena bahagikan load yang dekat sini bahagi dengan value strain. Okay, so value strain ni awak kena convertkan jadi bahagi dengan 100 lah. Jadi 0.0135. Okay, dapat load kat sini berapa bahagi dengan yang ini. So dapatlah dia punya secant modulus. Alright, find the change in length for yang modulus case and secant modulus case. Dan D ni kita boleh guna formula change in length divided by original length. Okay, so untuk kita cari change in length, okay, kejap. Untuk soalan D, kita kena guna formula strain sama dengan change in length divided by length. So kita akan dapat cari change in length sama dengan dia punya original length dia 5. Kita kena times dengan change in length yang ni, strain dia 0.0135. Okay, so darab lah 5 inch dengan 0.0135. Kita akan dapat 0.06. Calculate error introduced by using yang ni awak kena calculate error dia. Awak kena kira formula yang sama juga yang awak dapat dekat D. Okay, which is strain is change in length Awak dapat cari dia punya chin length dia sama dengan 5 inch times with 0.011 dekat secant modulus ni. Awak dapat secant modulus ni berapa, and then awak kena darab dengan 5. Okay, so ada dua jawapan lah dekat D ni. So bila dapat dua jawapan dekat D, awak boleh klik lah dia punya error, berapa persen dia punya error. So kita akan dapat 19%. Okay. Structural design in bending and flexural stress. The bending or flexing a plastic part induce both tensile and compressive stress through the cross section. As shown in this figure, okay, this is the tensile and compressive stress in bending. So bending actually it creates tensile stress on the convex side of the part and compressive stress on the concave concave side. So the neutral plane defines the plane of zero stress in which the stress magnitude switch tensile to compressive. Kita tengok dekat sini tensile stress dan dekat sini adalah compressive stress. And ini dia punya neutral plane. Okay. The stress distributed through the thickness of the part is defined by formula MC which is I represent the moment of inertia, C represent the distance from the neutral plane to the point of interest, M is represent the bending moment height over the beam. Okay, in this formula, okay, for the simple cantilever shown in figure the moment of inertia indicates the resistance of the bending and has units of length to the fourth power of inch meter. Defining section modulus sine of SI divided by C allows the bending stress formula which is stress P equal to M over Z. Okay, bila awak nak pakai formula ni? Kita ada calculation, soalan calculation ini. Okay. Okay, ni table ni pasal apa? This is the section properties for bending. Okay. The cross-sectional shape of plastic. H is the area width, height, and C H over H over 2. Dia punya neutral plane dia. Moment of inertia. Okay, sekarang dah bagi dalam table ni siap-siap. So, kita kira dia punya bending stress formula lah. Kita bagi dalam bending stress formula siap-siap. So bending stress formula are highly dependent on boundary condition. Macam dekat dalam table tadi, dekat table sini kalau kita tengok formula for the cross sectional area distance from the neutral plane to the outer surface in tension C, the moment of the inertia I, and the section modulus Z. Okay, various cross section. Okay, dash line dia ni, okay, dash line is the cross sectional diagram denotes the neutral plane ataupun neutral axis. So the formula assume the bending moment is applied about this axis. So the cross section that are not symmetrical about the neutral axis require some substitution of A and C to calculate I and C. Okay. So bending stress